Okay, so before I talk about angular momentum in quantum mechanics, I'll have to discuss what angular momentum is in classical mechanics. In classical mechanics, angular momentum is defined as the conserved quantity that arises when your system has a symmetry under an infinitesimally small rotation of the coordinates. And this conserved quantity is described by Noether's theorem under this symmetry here. So first off, we need to describe how a coordinate transforms under an infinitesimally small rotation. Let's say that there's a rotation about a particular axis. We're going to abstractly use the coordinates A, B, and C, where A, B, and C are any combination or permutation of X, Y, and Z. And we're going to say that it's going to be invariant our system's invariant under an infinitesimal rotation about the C axis. There's a gnat flying around. And for these purposes, I'm going to do a counterclockwise infinitesimal rotation. It won't end up mattering too terribly much. Well, viewed pole on, your C coordinate won't change, but there'll be a rotation in the AB plane. And we describe rotations, the changing coordinates due to rotations, with a rotation matrix. Let's get that. Cosines. And of course our C coordinate doesn't change under this transformation. So our angle of rotation, delta theta, is very small, and we only want first order terms of delta theta. So with the small angle approximation, cosine would just be 1 minus delta theta squared over 2, but we don't want the second order terms, so that's just going to be 1. And for the sine terms, it's just going to be negative delta theta. Negative sine of delta theta is very small, it's just delta theta. And that can be proven with the Taylor series expansion. So writing this out. And we might as well go write that C equals C. So our position vector changes like this. Our original position vector, our unrotated one, is just A, B, C, plus our fluctuation is just delta theta, negative B, A, C. And that's our new position vector. Oh wait, 0, negative B, A, 0, sorry. Well, we can write, okay, so we're going to write that as the replacement of our epsilon. So we can write this as a cross product between two things. Equals the cross product of the vectors 0, 0, 1 times A, B, C. Alright. So now we can write our A, B, and C is just our unrotated position vector. And 0, 0, 1 is the normal vector in sub C pointing out of the AB plane in the direction of the C axis. So when you take the I component of this, our fluctuation is just xi the I component of this vector here, this cross product. And this must be our q sub I in the equation. So we're going to differentiate with respect to q, delta theta and take that to 0. Well, that's just a 1, so we don't have to take the limit. And then our conserved quantity is just sum over the i's well, this is just a dot product between the vectors these vectors. And this is, as we defined before, our momentum vector. So we're just going to call this P arrow dotted with the normal vector in the C direction crossed with our position vector. Well, there's an identity. A dot with B crossed with C is equal to B dotted with C crossed with A. So we can rewrite this as R, with A being P and B being in sub C and C now being R. We can rearrange this as in sub C dotted with R crossed with P. Forgot an arrow. But when you cross, in our case, this is 0, 0, 1, you're only going to get the C component of this. Because these are 0. The A and the B components are 0, so the only thing that'll survive is the C components. So it means that if putting all this together, If our system has this symmetry under an infinitesimal rotation about the c-axis, then the c component of the vector, which is the cross product of the position vector with the momentum vector, is a conserved quantity. And that argument applies to if you had chosen A or if you had chosen B. In general, if there's a rotational symmetry about all three axes, then the vector, which is the cross product of the position vector with the momentum vector, is conserved and doesn't change in time, and this is called angular momentum. And there we go.